Okay, so thank you so much for having me here today. So this is joint work with Christine Palour, and please feel free to interrupt me at any time. So I don't think I have to talk too much about DeFi, but what we find interesting about Uniswap is that most modern exchanges are kind of a limit order book. And that seems to be the gold standard. Everybody sees this as the best way to provide liquidity. And when we went into this, I must admit that I thought this will mostly be a paper about why Uniswap is bad and why it doesn't work. But as it turns out, after spending quite a bit of time on this, I think we argued that this could be a really superior way to provide liquidity um, in a market, and that it can actually beat the limit order market. So let me just quickly talk about Uniswap. So decentralized swap facility started in 2018. No owner, no listing requirements. There's many clones of that we see today, SushiSwap, PancakeSwap, and all the other ones. Daily trading volume, well, that depends a little bit. This is a little bit dated, so now it's much less. It's a little bit quieter in the crypto winter, but this was a huge market, and there's a lot of liquidity locked into this. So how does this work? The agents deposit liquidity into a pool, and they deposit two tokens in proportion to the existing pool. So whatever the proportion in the pool is at the moment, this is what the liquidity providers inject into the pool. In return, they receive a liquidity token. So the pool then changes as users trade. The pool collects fees from trading, and at any time, the liquidity providers can withdraw liquidity. So by redeeming the liquidity token, and then they get whatever is in the pool at the time. And so this could be a different mix of tokens and that they get back when they withdraw liquidity rather when they put in liquidity. So the way this works is that for any trade, so in our example, we have one token called ETH and the other one called token T. And so at any point in time, when you trade any amount delta E and delta T, it has to be that the point after in the state of the liquidity pool after the trade has to be a constant. The product of the two inventories has to be a constant K. So specifically also if you don't trade at all, this is how the constant is defined. So if the delta is a 0, then we can get K from this simple equation. So graphically it looks like this. So you have the two inventories on the y-axis and on the x-axis, the ETH and the token. And then we are currently at some state T0, E0. And so that defines the point on this bonding curve. If we plot this equation, we get this black line. So if somebody sells some tokens to the pool, then the inventory of tokens goes up from T0 to T1. And how much ETH does the trader get in return? Well, that is from E0 to E1. We can see here along the y-axis how much the trader gets back for selling these tokens.
Can I ask you a question?
Yeah.
What's your thought about the use, like that most of the protocol use the product instead of maybe using like a log function or different function? Like, do you think like there is a good reason to use this specific function?
I think there's no good reason to use this specific function, and maybe other functions could do better or not, but I think that the function is much less restrictive than people think, because what is really the key variable that we want to focus on is the size of the pool. And as the size of the pool changes, that curve flattens, right? So I think the key research question from an economic side is what is the size of the pool? And that gives you a lot of freedom in how this function really looks like. So
Yeah, thanks. Makes sense.
okay, so let's look at we build a little microstructure model, and all the details are in the paper, but I just want to give you the main intuition what we do. So we have an asset with price P0, and there is either no information event, in which case the price stays constant, the fundamental price of the token. And in that case, a liquidity trader arrives and trades some exogenous amount Q of tokens. Or there is an information event, in which case the true value can either jump up or down. So the value could either probability alpha over 2 can go up by an amount sigma, or it with the opposite probability can go down to P0 minus sigma. So there's an informed arbitrageur in the market. And so if the arbitrageur sees, for example, that the price of the token went up, then she's going to buy the token and see if there's any positive value trading opportunities, potentially buying the token at some kind of price and then selling it at P0 plus sigma. So everybody is risk neutral in our model. So to simplify the math. So we build a stylized model of the limit order market, which is kind of a simplified Kyle type model setting. But the innovation that we have is we have two competing liquidity providers. So if both liquidity providers are in the market, then we have a similar outcome than in the Kyle kind of framework. The only difference is that we have a mixed strategy equilibrium where the two liquidity providers offer a probabilistic schedule of prices, but then the main result that they break even on average is the same as in the Kyle framework. So there's nothing too exciting going on if both liquidity providers are in the market. I think what is new is that we allow these liquidity providers to invest in the technology that gives them some chance to become a monopolist. And we can think about this as just being probably just a little bit ahead of other traders. We can think about high frequency trading. We can have these liquidity providers then that are successful with this technology. They learn whether a large institutional trader like Fidelity is placing an order, and then they can exit the market or adjust their quotes ahead of time in a profitable way. That we learn information about price movements faster than others, or something like this. So this monopolist liquidity provider in our model very simply charges a really high spread, and because she's a monopolist, she can extract that rent from the traders. So the technology is wasteful and costly. So from a societal perspective, that's not something that we really want to have. So let me just give a quick summary of the sequence of events in the limit order market. So we have these liquidity suppliers who invest in this monitoring technology. Then nature allocates these liquidity suppliers to a market, meaning that they either are in a competitive environment or that they are monopolists. Then these liquidity suppliers post optimal quotes, optimal orders. Nature draws whether there is an innovation in the price or not, and then either the liquidity trader or the arbitrageur trades. So let us contrast that to the UniSwap framework. So in the UniSwap framework, the liquidity suppliers commit capital to a pool. So the pool size is determined. Then either an innovation happens. In this case, the arbitrageur comes in and sees that there is a trading opportunity. Or if there's no innovation, then the liquidity trader arrives, trades some amount Q of units, and then potentially the arbitrageur looks at the state of the liquidity pool and trades after that. So let me talk a little bit in more detail about these two cases. So keep in mind that the liquidity providers always earn some kind of fee per trade. So on Uniswap, that's 0.3%. In version 2, version 3, we have different pools with different fees. But so let's go back to what happens if there is no change in the true price. So if this liquidity trade arrives, so let me go back to my picture. So that matches pretty much with this picture. So the state currently is E0, T0, and that's also the fundamental price. This is the true price of the token. So now this liquidity trader trades and pushes the price away from the fundamental price. So now we have E1, T1. So what happens then is that the arbitrageur comes along and pushes the price right back. So since all the trades are along this bonding curve, nothing really bad happens to the liquidity providers. They just move from here to here, and then they move back where they started from. So the liquidity providers have the same inventory as they had before, but they collected 2 times the trading fee, which is actually great for the liquidity providers. They made really a killing here, and they collected 2 times the fee, and there was no movement in price. Now, if there is the movement in price in the fundamental value of the token, then of course let's assume that, for example, that the true price now is E1 over T1, then the liquidity pool quotes a stale price. And because it's just a computer program, even though we call it smart contracts, it's not that smart. So it just quotes a stale price. So the arbitrageur will see this and take advantage of this mispricing, and the pool gets picked off, and the liquidity providers lose out. So this is where the liquidity providers are hurt. So we then look at the equilibrium in the limit of the market, and in the pool, so in the limit on the market, there's 0 expected profits when both liquidity providers are in the market. There's monopoly rents if they become a monopolist. So therefore, there's an incentive to invest in this extra technology, this high frequency trading technology that allows you to become a monopolist. And in the paper, we derive an equilibrium amount of this, and then we can figure out what's the cost of trading for a liquidity trader in this market. So in the AMM, let me come to our kind of equilibrium concept. And I think this is one of the big contributions of our paper, that the pool size adjusts endogenously in such a way that the fee revenue is equal to the picking off risk. So the fee revenue is kind of, we can see that if the pool grows larger, then the fee revenue goes down. So we see that the more people are in the pool, they're all going to share this fee revenue that comes from the liquidity trader. So kind of as the pool grows, that fee revenue goes down. But this picking off risk is pretty much constant, because if the pool increases, then just the arbitrageur trades larger amounts. So the arbitrageur optimally picks the size of the trade if the AMM quotes the stale price, and the size of the trade depends on the size of the pool. So this is pretty much proportional to the size of the pool, and so there is an optimal equilibrium size of the pool that comes around here. So why is this important? That the pool size determines the price impact. So smaller pool size means that kind of this bonding curve is more kind of curvy, and so that means that there is a higher price impact.
Can I ask a question?
Yep.
So about the fee revenue, so I guess that pools have a different liquidity fees, and most of the time the argument is that if you have stable coins, pools with less price impact, so the fees are low, and when you have riskier pools with more price movement, so you have a higher fee. So can you do you think it's I guess the market make it be like that, but do you think this is also one force that explain the first point, or it's?
I think I mean, the fee consists of two parts: the effective fee that you're going to pay, right? So when you trade, so your effective trading costs consists of two parts. So that is the official fee that you're going to pay to the pool for trading, which is based on volume, plus um, plus the price impact that you're going to have when you trade. So obviously, if there is if you have a pool of two stable coins, then the pool can be very large, so that your price impact is practically zero, and therefore all you pay is that fee revenue. And so because that picking off risk is very small. But if you think about it, then if you keep the fee percentage kind of constant and say you charge 0.3%, that just means that if the pool will get very large, and so the price impact is low, but for the individual, because the pool is so large, the individual kind of dollar fee revenue for a liquidity provider that provides $1,000 of liquidity, that fee revenue is going to be small. So if we adjust the fee here, then we have to think about also what will happen to the optimal size of the pool. And so we could charge a smaller fee, but then the pool size would be smaller, which means that the price impact will be larger. So there is a clear trade-off on total trading costs. Let me just mention that one thing that we also think is important is that we include the arbitrageur trades here at the end. So you see other papers that stop pretty much here after the liquidity trade, and then they say, well, now the price is kind of different from what is in the market, so the liquidity provider can withdraw liquidity and pocket the money or make some profit or something like this. That is not really consistent with what we see in the data. So we don't see that liquidity providers withdraw liquidity very quickly. And so what we see in reality is that the liquidity is fairly stable in these pools. And so what happens then is that this kind of adjustment, when the liquidity trader pushes the price out of equilibrium, that profit from adjusting to the fundamental price goes usually to an arbitrageur. And very often that's part of an MEV trade with flash bots or something. So that's very immediate. It follows very often directly the transaction of the liquidity trader is the arbitrageur right afterwards who pushes the price back. So. Okay, sorry, confused where I was. So here. Okay, so let me talk a little bit about the data that we have. So we have all UniSwap V1 and V2 liquidity pools. We look at factory contract transactions where these pools are created. So we have about 76,000 liquidity pools. Most of them are V2 pools. And we have 83 million transactions on Uniswap from the beginning until July 22. There is 1.8 million liquidity injections. There's about 900,000 withdrawals of liquidity and 79 million trades of tokens. There's some complex transactions as well in there, so flash loans, flash swaps, and other complicated transactions. So that makes up the rest to the 83 million. So if you do look at the data, there's a lot of interesting data difficulties here. So some tokens copy the ticker name of USDC, but they're fraud. A lot of these high volume transactions are driven kind of by exploits. So the highest volume was $18 billion in March 21. The largest trade in our example was where somebody swapped 48 million DAI for about 300,000 ETH. sorry, this should be large volume trades that are linked to exploits. For example, somebody swapped here $23 million of wrapped ETH for Unibomb tokens. And the exploit was that Unibomb is a token that burns 1% of each transaction. So what the trader did was the trader traded back and forth many times the token. And then what uh, the there was another protocol that didn't realize really that this burning happens. So they were quoting stale prices. And so the trader could then trade at this stale price and then called an update function that made the protocol look how many tokens you really have. And then the protocol found out that all these tokens had been burned. And so now the kind of price adjusted very dramatically, and so therefore that exploiter made a lot of money from that trade. So this is one of these large value transactions, and there's quite a few of that. So measuring volume is not so straightforward. So there's no clear numeraire in this kind of environment. So we use ETH as numeraire and then convert that to dollars. A lot of the volume is hard to measure because of flash swaps. So what is flash swap? Flash swap is a flash loan and a token swap. And let me just quickly highlight this. Transactions in Ethereum are atomic, so we can either execute the transaction as a whole or it fails. So we can go and borrow funds at the beginning of a transaction and repay them at the end of the transaction. So because it's an atomic transaction, there's no credit risk for the lenders because they give the money and they get it repaid at the same time, same instant in time in the same transaction. So therefore the borrow only happens when the repay happens. So in Uniswap, it's a little bit more complicated because we can repay any combination of the two tokens as long as the value of the repay is the same as the value of the borrow. So this can lead to some unusual kind of problems when measuring volume. So there was, for example, somebody created in March 21 a token called Scammy, and they created a Uniswap pool. Then they borrowed $220 million in a flash loan, and they traded back and forth between wallets that same token, that Scammy token, up to a volume of $5 billion, and then they repaid the flash loan. It was not totally clear why they did this. Maybe just to demonstrate that a lot of the volume data that you get on Uniswap is nonsense. But so if you look at uniswap.info at the official Uniswap website, that 5 billion are missing in that graph that you see there. So, but if you look at the raw data, you can find that trade. So here are the largest. So we do a little bit of filtering and try to filter out these pools that exist only for a few days, or have very few trades in them. So if you look at the largest pools, this gives you a little overview. So on V2, we have a lot of the large pools trade wrapped ETH and some form of stable coin. So we have here wrapped ETH against USDC, wrapped ETH against Tether and DAI. And then we also have here Fei, for example, and then wrapped Bitcoin is also a large pool. So that is kind of consistent with this idea that that people like to often build up levered positions, and we have another paper on DeFi lending where we show some evidence that this seems to be the case, that people borrow more coins against their ETH and Bitcoin, and then use that to build up levered positions. So that would be kind of consistent with this idea. Similar picture in V1, but the volumes are much smaller. Of course, all the numbers are much smaller in V1. So this shows you the number of trades per day. So we see that in the beginning we have V1 in blue, and then over time V1 went away as V2 came along. And so in the orange part, we see V2 transactions against wrapped ETH, which is the dominant trading pair, and the red part shows other token transactions that do not involve wrapped ETH. So most of the trading happens against wrapped ETH, and if you look at the volume, then it's even stronger. So this picture shows you the
Can you go
question.
back to the previous slide? So here, like the big drop in the number of transaction is due to version 3 or the market collapse?
I think first we see the market a little bit go down, and then it is version 3 taking off. So we do understand that our results are somewhat limited by the introduction of version 3. And I said that I would talk a little bit about why our results still matter for V3 as well. So this idea of the optimal pool size and price impact, that still matters in V3 as well, that kind of trade-off. In V3, you provide liquidity in a more narrow band. So there's kind of two major innovations for V3, that you provide liquidity in a narrow band and that you have different pools with different fees. So I think, but the basic trade-off, how much do I expect in fee revenue versus what is my peaking off risk, that same trade-off applies in V3 as well. It applies more locally in that within that band of liquidity that you provide. But I think the same trade-off is true there as well. Just the fact that we have these liquidity bands makes the empirical exercise much harder. But I think the same kind of economic principles apply there too. So if you think about the special case of V3, where we provide liquidity for the entire band, then this would be like V2, right? So therefore, I think we have the same trade-offs, but it's just slightly modified because it gets reduced to a smaller band.
Thanks.
So this picture shows you the amount of the network of these Uniswap liquidity pools. So the size of each node corresponds to the number of pools that trade against a specific token. The color represents the depth of liquidity that's staked in a particular token, and the thickness of so if there's a line, that means there is a pool between those, and the thickness of the line depicts the trading volume. So what you see is that in a way, this represents what we know about financial networks in general. So if you think about financial markets, these often form core periphery network structures. And so we have something similar here, where we have a core of wrapped ETH and the stable coins, and then the pools connect to this kind of periphery, and the pools, these individual tokens, are not very connected amongst each other, but they mostly are connected to either one of these core tokens that are in the middle of this graph. So one of the key predictions of our paper is that the pool size is kind of decreasing in innovation and price and increasing in uninformed trading. So let me show you first the innovation and price proxied by the volatility of the token price. So when we find indeed that if the token is more volatile, then we see that the size of the pool is generally lower. So that is consistent with this kind of sigma in our model going up. We do control for airdrops, because some of these Uniswap, there was a uni airdrop of the uni token, and we find that pools that were affected by this airdrop are larger because people just invest in this pool because they want to collect the uni token. So that just control for that. The volume. So we have 3 proxies for uninformed trading, and one proxy is volume. In Uniswap, like in the stock market, you traditionally try to hide your orders in order flow, and there's businesses that just chop up large trades into small trades and hide them in the so that you can kind of pretend that large institutional traders make them look like retail trades and things like that. So that's not really necessary in Uniswap. So we can trade straightforward. So therefore, we argue that there's a certain amount of volume that's based on information in a given day, and any extra volume must be uninformed trading. And so if you buy that story, then we can see that larger volume coincides with larger pool size. We also have a similar line of argument for the number of trades, because there is no incentive to chop up your trade into smaller trades. Then we argue that again that there's only so many trades that are based on information on a given day, and any extra trades are based uninformed trades. And so again, then if there's a larger number of trades, then we should see this. We see that this pool is larger. And finally, we have a measure of direct evidence of uninformed trading. So these are reversals. So what is a reversal? When, say, a trader trades and right afterwards there's an arbitrageur who trades in the opposite direction. So we can trace that in the data and see when somebody trades in one direction and immediately afterwards is a trade of similar size that is in exactly the opposite direction, then we argue this is an arbitrageur. So this fits the story of an uninformed trader coming in, trading something, and then the arbitrageur doing the opposite trade. So we look at this and count the number of these trade reversals that we see, and we find that that this is indeed proportional to the trade size. So that means that if there's more uninformed trading, then there's more fee revenue, and that means that the pool gets larger.
Can I ask a question?
Yes, please.
So it's very interesting, but do you have maybe data about number of traders, like private wallets? Because this is something that I find very interesting, that many times we have only few traders that trade like a bunch of trades in some pools, which make it be also interesting if it's also can influence the pool size in some sense.
That's a very good question. We do have the data. I didn't look at it yet, but I would guess that this arbitrage activity is very concentrated, right? So if we think about the tech, and we look at this in our DeFi lending liquidations paper, and we find that these loan liquidations in DeFi are very concentrated amongst very few bots. And I would guess the same is true here, that there's very few wallets which are kind of arbitrage bots that run all these arbitrage trades on Uniswap. And you need to be pretty sophisticated. It's based on you often make a private side payment to the miner. It's to get right in after the trader. So you go through something like Flashbots or some interface like that. And so it's pretty sophisticated, I guess. And so there's a lack of talent, a limited pool of talent, and so we see high concentration of these traders.
I have a question. So can you explain a little bit about the intuition here for increasing in uninformed tradings? Because you would thought that, you know, if you want the pool size to be large, then for every trade, the impact will be small, then there will be less, you know, arbitrages opportunities. Then the pool size, when the pool size gets larger, these uninformed trading. When there's these uninformed tradings, you would like to have smaller pools, so there are arbitrage opportunities that you can collect fees from the trades, or?
Well, I think the arbitrage opportunity is still the same, right? So if any positive arbitrage opportunity will be taken. Let's put it this way, right? So if the pool is large, and that means that there's only a small arbitrage opportunity, fine. I mean, yes, it's bad for the arbitrageur, but on the other hand, costs of this, once you write the code for the bot, it doesn't really matter. Then the bot just makes $5 instead of $500, but they will still make the $5 because the bot is out there. So any arbitrage opportunity will be taken, and the liquidity providers just care about the trading volume, right? So they collect based on the volume, and so that is irrespective of price impact. So in a way, there's no loss for the liquidity providers, but it's true that the arbitrageurs make less. But I think it's not that there's such a strict cutoff. As long as there is some positive value, the ARB bots will come in. And I think you see in the data, I looked at some of these arbitrage trades. I looked at trades where the ARB bot made like $10, which is not huge, but once you've written the code, if you make 100 times $10 a day, that's not bad either, right? So and so one thing that we wanted to look at is, because some of the papers in the literature argue, as I said before, that the liquidity providers then withdraw liquidity if the price is out of equilibrium in the pool. And so we looked at how stable is this liquidity provision, and we find that this is actually very stable. So only about slightly more than 1% of our sample are liquidity withdrawals. There is 1,800 events with the same address added and withdrew liquidity within 50 blocks. And the median size of this is $146. So my guess is this is people just trying this out and saying, okay, let's try this. If I inject some liquidity and I withdraw it, do I get my money back? And so it's more like testing this. So we only have 18 observations where there is a deposit and withdrawal of over $1,000 within 5 blocks. So this is what I would think of high frequency liquidity provision. So that's not really there on Uniswap. In fact, so we looked at a specific day in our sample, so May 19, 21. This is when the price of ETH against the US dollar dropped by 40%. So to give some context to this, this is about twice the size of the 87 stock market crash. And so we collect high frequency data on the price of ETH to US dollar. So you see that in the kind of orange area in the back. And this is the cumulative, the blue line shows you the cumulative liquidity flow out of the US dollar ETH liquidity pools. So we aggregated the main pools, DAI, Tether, USDC. And what you see is that liquidity provision was actually very stable. So in total, about 17% of liquidity was withdrawn. And when ETH hit really the bottom, at that time, only 2% of the liquidity was withdrawn. So if you contrast that with a major crash in the stock market, where all of a sudden all the liquidity is gone, no market maker wants to pick up the phone. So here we see that this market actually works very well in a crisis situation because there was a lot of liquidity provision. Now, you could say that the liquidity providers were kind of late in the game. Yeah, that's kind of a behavioral assumption. I don't know how you really justify that. But one thing we do see is that the fee revenue went up a lot during this crisis. And so, yes, it is true in some way that these liquidity providers suffered some losses when the price went down because they had to sell at stale prices. But on the other hand, there was so much volume that they really got a lot of the fee revenue. So they actually that made up a lot of the losses.
But can I ask you? I think in the past I watched a lecture of you speaking about the movement from V2 to version 3. So this is kind of an example that version 3 will not be so good in the way of liquidity thickness in a crisis, right?
Right. Yeah, I agree with that.
Okay.
I think that's true.
Okay.
So,
and I think this is like the problem of the complexity of V3, that people will become more sophisticated. So there is no the incentive of saying, okay, let's stay 5 years with at the pool. I don't carry the money, the prices will move, but I will get a fee for I can be passive. Like I don't need to update.
that is absolutely true. So I think that the complexity is a deterrent to invest in V3. So I always tell the story that I could not be a liquidity provider in the New York Stock Exchange because I'm not sophisticated enough, but I can be a liquidity provider on Uniswap, and so. But I'm a V2 liquidity provider. I'm not a liquidity provider on V3 yet, because again, I would have to understand how this system works, and I'm up against some much more informed players, more sophisticated players. So I will face adverse selection and I will lose out. So that's a real concern. So I think in that sense, just V3 is not all great, because there is some this passive liquidity provision, I think, is a real asset of V2, and so I guess we'll see where it goes. But so we look at compare that to a centralized exchange. So we look at tokens that trade both in Uniswap and on Binance. So we identify 384 tokens, but most of them don't have a lot of trading volume. So we end up with 27 tokens. We thought that the prices would not match very well because it takes time to transfer tokens out of Binance or into Binance. And so the other thing, on the other hand, on Binance, you can trade instantly, versus on Uniswap, it takes 10 seconds or 15 seconds for the next block to arrive. And then there's a little time delay there. So when we looked at price matching, it actually works pretty well. So what you see here is the pricing area in blue that goes with the right axis. And initially, as the pool size is the orange area. So and that's on a log scale. So as the pool started out, obviously pricing errors were huge. But as soon as the pool size hits about 1,000 ETH, then the pricing error is close to zero. So it matches very well how prices trade on Binance and Uniswap. So this is for USDC ETH. So this picture shows you a random day of how prices evolve on Binance versus Uniswap. And again, we see that the prices match fairly shortly. So fairly closely. So we do see that Uniswap pretty much follows and Binance are close together. So the two questions come up here sometimes. So who is first? Where does price discovery happen? Does it happen on Binance and then Uniswap lags behind, or is it the other way around? So it's hard to say. We do have another paper on DeFi liquidations where the event that triggers a price change clearly emanates on the blockchain. So if you liquidate a DeFi loan and then the liquidator sells the collateral on the DEX, then we have a news event that clearly emanates from the DEX and not on Binance. And we see that in those cases, Binance prices also follow the DEX pretty closely. So I think it's both. News events come from both sources, and so it's not totally obvious that Binance provides price discovery and Uniswap just follows. I think that's not really the case. So this is our kind of key picture, and so in the model, because what we predict is that in the limit order market, we see a higher price impact, and we also see a higher price variation. So intuitively, this comes from the fact that this liquidity provider can sometimes become a monopolist, and when the liquidity provider is a monopolist, then she charges a very high spread. So then the price impact is huge. If she's not a monopolist, then the price impact is much smaller. But then just so we have more variation in price impact, and on average, our model would also predict that for some regions of the parameter space, we do have a higher price impact on the limit order market. So we do find this confirmed in our data. So this shows you the price impact of USDC CE on Uniswap, which is the orange line, so that's our empirical measure. We can also measure price impact on Uniswap theoretically. We just take the derivative of this bonding curve at the state that we are in, so that's the green line. And we contrast that to price impact on Binance, and we see that there's a much larger price impact on Binance, and there's also more variation in price impact on Binance. So here we look at trading volume of Binance versus Uniswap. And what we see is that initially, of course, when Uniswap started out, all the trading was happening on Binance, and then more and more volume moved to Uniswap. And more recently, kind of that went back a little bit. And I think there's two reasons for that. First of all, Binance was under so much pressure, the way I at least see things, that they created Binance Smart Chain with the main purpose of deploying PancakeSwap, which is a Uniswap clone. So they decided they cannot compete, so they better copy whatever Uniswap is doing on their own terms. So that made a lot of volume go back to Binance. And the other thing is that V3 came out. So I expect that this is the most popular trading pair on V3. So we see a lot of volume being moved to Uniswap V3 rather than V2. So we also look at pricing errors between those two markets, just as a kind of interesting exercise to see if this confirms our intuition. And what we see, for example, is that obviously if the pool is larger, then the pricing error goes down because there is more. There is less price impact. If the volatility of the token goes up, then the price impact is larger. We see that the trading volume is so we measure if in general there's more trading volume for tokens, then we see that the pricing error goes down. And now when we look at the relative distribution of trading volume, we see that there's some kind of a U-shaped pattern here. So that what that means is that the pricing error is smallest when trading is kind of 50-50-ish between the two exchanges. So when the trading volume is more evenly distributed, we see that the trading volume is then best. So the last thing we see is that the gas price plays an important factor too. So when the gas is very expensive, we see that pricing errors are higher, and when price impacts are higher, we also see that that the pricing differences are higher, which also makes sense because then arbitrage is harder to do. So to conclude, I hope that I could convince you that we this new model of liquidity provision, that there's a lot of things, that it has a lot of things going for it. That our argument is that the liquidity providers in the limit order market have an incentive to invest in some wasteful technology to carve out some competitive advantage, but in a pool, these address selection costs get mutualized, and that reduces the cost to post liquidity. And therefore, there's some regions of the parameter space where the pools can dominate the limit on the market. I think one of the key ways how this benefit manifests itself is that these pools can have lower price impact and lower variation in price impact. And we show that theoretically and also confirm that in the data. That was it. Thank you so much.